Hello, I am VAUDAINE, a PhD student from the Hubert Curien Laboratoire in Saint-Étienne, France. Today, I will present to you our work with Christine Largeron and Baptiste JEUDY on the detection of contextual anomalies in attributed graphs. First, in this illustrative example, we have a graph with some companies A and B, which have a revenue greater than 10, a CEO, a CTO, an employee, and a fraudulent accountant. Company A has been tagged as an anomaly by an expert, and we wonder whether Company B should also be tagged as an anomaly. To answer this, we will train a model that learns to detect such anomalies by assuming that they are induced by a specific local context, such as being a rich company with a fraudulent accountant. These anomalies are contextual anomalies. Contextual anomalies are nodes of the graph whose local context or neighborhood exhibits a singular arrangement. For example, here, context 1 is defined by the node having no specific color and one of its neighbors being green and the other blue. It is denoted by B and G. Context 2 is only the node itself with the color yellow, and context 3 is the node having color blue and one of its neighbors being green. More formally, let GVEX be a graph on a set of nodes V, a set of edges E, and a feature matrix X. We consider that there exists an unknown small subgraph, a context, and a distinguished node in this subgraph, such that each time this subgraph occurs in the data, then the node corresponding to the distinguished node is an anomaly. As you'd expect, we are not the first to study graph anomaly detection. It has many branches. Two of them are anomaly detection in graphs without or with features. We can divide the first kind into three subparts: graph clustering algorithms that aim at finding bridges between communities, or algorithms that focus on structural anomalies such as anomalous edges or irregular subgraphs. And finally, a particularly interesting model is Oddball, which finds laws to detect nodes which do not follow those laws, such as near stars, near clicks, dominant edges, or heavy vicinities. The second branch focuses on finding nodes whose features deviate a lot from those of their neighbors. On the graph below, we can see the red arrow that indicates a node whose features, 0, 0, do not correspond to the features of the node of its community in green. But none of the different approaches shown here is able to deal with contextual anomalies that we study in this work. To identify this kind of anomalies in an attributed graph, we use graph neural networks in a semi-supervised settings. So, graph neural networks are a class of deep learning models that aim at performing inference on graph data. The main idea of GNNs is to learn a mapping function f, a so-called aggregation function, such that the new representation of a node is a combination of the previous representation of its neighbors and itself. For example, on the graph here, the new representation h'0 for node 0 is a combination of the previous representations from h0 to h4. The choice of the function f influences a lot the ability of the GNN to perform certain tasks. Thus, many designs have been proposed in the literature. Let me introduce a few of them. GraphSage is one of the first which has been made. It comes with a few different aggregation functions. One of them is the mean aggregator. It simply averages the previous representation of a node I and its neighbors j and multiplies it by a linear transformation w. Then GCN, or graph convolution networks, have been proposed to tackle the issue of graph data in a similar way as usual convolution networks do with images. The new representation H' is the sum of the previous representation of its neighbors weighted by their degrees. Graph attention networks, or GAT, are one of the best solutions to do classification on graphs. The new representation h prime I is a linear combination of the previous representation hj of its neighbors and the weights alpha aj of the linear combination are attention weights and can be learned. Our main issue is that there is no dataset with such anomalies available. We are had to create them. To do so, we choose a context and a graph. Then each node is attributed a one-hot vector, which corresponds to color in our case, but it could also correspond, for example, to the role of a person in a company. Finally, each node is assigned a class, anomaly, or normal node, depending on its context. Here are different contexts we use to create anomalies, but we can imagine many more of them. So each letter corresponds to a color or a one-hot vector. A bar above the letter B means that the node has to be blue in order to be tagged as an anomaly, and if there is no bar, it means that it requires at least one of its neighbors to be blue. For example, A4 is Y bar and B. This means that every node that is yellow and which has at least one blue neighbor will be tagged as an anomaly. And please note that the definition is only used to create the dataset and is never used while training or testing our model. So let's take an example, and here we choose the anomaly context A4. Then we will choose a specific graph. We'll then give a color as a one-hot vector to each node. And finally, nodes are tagged as anomalies or normal nodes if it is yellow and have at least one blue neighbor. So in this case, we have two anomalies. So we used different kind of graphs in our experiments. Erdős-Rényi, Dancer, and LFR are generated graphs. This allows us to have a good control of the different aspects of the graph, like communities, distribution of degrees, and so on. And Facebook, Pollblogs, and Quora are usual datasets of the literature. So, now that we have created our datasets, let's see how to detect the anomalies. Scopage is a context-based graph anomaly detector whose main idea is to learn two classes classifiers with attention mechanism in a semi-supervised setting. This means that some nodes are tagged as anomalies or normal nodes, and some other must be classified into one category. To do so, we proposed an extension of the GET network. The one of the differences is the first step, where we transform the input features, the one-hot encoded colors in our case, into features of lower dimension. Then, the second step consists in the usual linear transformation for each attention head, where we learn WC. The main change is the way that we compute the attention weights. In equation 3, the Adamant product between lambda IC and lambda GC is a measure of how similar these two vectors are. Then the dot product with UC selects the features that are relevant for future classification. Then we apply a leaky ReLU and a softmax layer to have our attention weights. The new representation for each attention head is given by the linear combination of equation 5, and finally, the concatenation of both heads gives us the output of the layer. So to show the ability of our model to detect contextual anomalies, we conducted experiments on every graph and every kind of anomaly context shown before. So to train our model, we use 50% of the anomalies and the same number of normal nodes. This allows us to avoid some issues of the classification in an unbalanced context. The validation set is made of 25% of the anomalies and as many normal nodes. And finally, we do not balance the test set as we do not have prior knowledge of its composition. Thus, it is composed of the remaining 25% of the anomalies and 25% of normal nodes. So we compare our approach, Copagad, with three challengers, GraphSage, GCN, and GAT. All of the details of the setup can be found, obviously, in our article. So here, we show the results of the 4 different models for the 6 different graphs with the anomaly context A4. So we train the models 12 times independently and choose the 3 best on validation. The results reported here are the average precision and standard deviation of the classification for the anomaly class only. We do not report the recall as it was nearly always 1, same for the precision and recall of the normal class. The numbers in blue are the best in column, so for each graph. And we can see that our algorithm performed very well with precision of the anomaly class close to 1 and generally outperforms its contenders. Here we show the same results for the anomaly context A4. Copagad still performs well with precision close to 1 and nearly always outperforms the other approaches. Copagad is consistent throughout their experiments and perform well regardless of the definition of the anomaly or the graph we use. So, finally, in this work, we clearly defined the concept of contextual anomalies and presented Copagad, a context-based graph anomaly detector. We also demonstrated its ability to detect such anomalies and to outperform state-of-the-art models. And then, to extend this work, we'd like to add interpretability to the anomalies found by Copagad. And we would also like to be able to score anomalies to help experts focus on the most important ones. So thanks for your attention, and it will be my pleasure to answer your question if you have any.